Welcome to Derivability. Okay, here we're going to take a look at some thermodynamics. Maybe you guys are taking some intro physics right now and studying thermodynamics. And you understand the concept of thermal equilibrium. Okay, maybe you're learning about the concept of entropy. Okay, second law of thermodynamics says that closed systems will tend to maximum entropy. Okay, so let's take a look at that. This is not fully general. Okay, the fully general version of this discussion, happens at probably a higher level than this, maybe in a statistical thermodynamics class. Okay, a lot more sophisticated, a lot more general. But let's just kind of get a hint of this from the standpoint of introductory physics, perhaps. Okay, so we know that in a closed system, the sum of all the heat exchanges are going to be equal to 0. Okay, some parts of the system gain heat. We might call that positive number. Some parts of the system lose heat. That might be negative. Okay, so if I have two components to the system, call them number 1 and number 2 here. Okay, and if they are undergoing temperature changes, okay, no phase changes, no first law issues where we have like volume expansions. Okay, just some very simple temperature changes. Okay, we know that the heat exchanged or gained, lost by a system is mass times the specific heat capacity times its temperature change. Okay, so the lowercase c here stands for specific heat capacity. Okay, now as it turns out in our work, this combination of mass times specific heat capacity is always going to travel together. So it's worth making a definition of something called the total heat capacity. I'll call that capital C, equals the product of mass times the specific heat capacity. Okay, so what we can do then is we can rewrite this equation here. Sometimes we call it the calorimeter equation. Okay, we can write that as the total heat capacity of system 1 or subsystem 1 times delta T. Okay, that's going to be the equilibrium temperature minus the starting temperature of system 1, subsystem 1, and then likewise for subsystem 2. Okay, C2, capital C2 times that temperature change. Okay, so what this does is this gives us a formula we can solve for that equilibrium temperature. Okay, and other than this being fully symbolic, this is probably not anything that's too new to you right now. Okay, you've probably solved equations like this. Okay, so the goal here is to solve for this equilibrium temperature. Okay, so you can see here I'm kind of marching toward that. Okay, so I can factor the equilibrium temperature from those two terms that contain that. Okay, so equilibrium temperature times C1 plus C2, and then putting the negative terms on the opposite side. Okay, C1T1 plus C2T2. So what I'm getting for this equilibrium temperature, okay, is going to be C1T1 plus C2T2 plus the sum C1 plus C2. Okay, so let's keep that in mind here. Okay, now again, that's not the point of our video today. Okay, but what we're going to do is we are going to consider the change in entropy of this closed system and show that maximizing the entropy always happens at this thermal equilibrium. Or really a better way to say it would be that thermal equilibrium maximizes entropy. Okay, so let me create a little bit of space on the screen below here, and then we'll continue in a minute. All right, now let's talk about the change in entropy. Okay, so for a system that's undergoing a temperature change, first we have to think about this infinitesimal change in entropy. ds equals dq over t. Okay, now that dq, we can write in infinitesimal form C dt, where that capital C is the total heat capacity, otherwise little m little c. Okay, and to get the change in entropy, we have to integrate over this from the initial temperature to the final temperature. Okay, C is a constant. I can bring that outside of the integration. Okay, so I end up getting C, and then times the natural log. And then when I evaluate between the limits, it's going to be natural log of T final minus natural log of T initial. Okay, and very often what we do in physics and engineering is we get this so we can write this as a single logarithm of that ratio. Okay, C times natural log T final over T initial. Okay, now what I have going is I have two parts to this system. Okay, so delta S total is going to be delta S for the subsystem 1 plus delta S for the subsystem 2. Okay, so again, if you were doing a more of a traditional problem, we could write this as, say, C1 times natural log of the equilibrium temperature over temperature 1, that is the starting temperature for subsystem 1, and then likewise C2 plus this logarithm of the ratio equilibrium temperature to the starting temperature of system 2, T2. Okay, but what I'm going to do here is I'm going to say, well, what if our system doesn't necessarily come to thermal equilibrium? Okay, so what if we don't necessarily come to thermal equilibrium? Okay, well, in that case, what we're going to have is we are going to have a final temperature, I call it lowercase t1 for system 1, and a final temperature lowercase t2 for system 2. However, T1 and T2 are not independent. We still have to obey conservation of energy. Okay. In other words, we still have to obey that calorimeter equation that we talked about on the previous screen. Okay. So what that's going to say is that C1 and then parentheses little t1 minus big T1 plus C2, and then likewise little t2 minus big T2 equals 0. So the capital T's are the starting temperatures for each part of the system, and then the lowercase t's are the final temperatures. Okay. So what I can do is I can write delta S for the system as C1 times natural log little t1 over big T1 plus C2 natural log little t2 over big T2. All right, and then to the extent that it looks like I have two variables here, little t1, little t2, they're actually related using this calorimeter or conservation of energy equation. Okay, so what I can do is I can solve this for T2 and then plug in for T2 here. So now we're down to just one variable in the entropy equation. All right, so let me create a little bit of space and then we'll keep going with that. Okay, all right, so what I want to do is I want to solve for this little t2 right here. Okay, so let me do this first. Let me just get things so that I don't have any minus signs, at least to start with. Okay, now this right-hand side, okay, if you go back and remember what the equilibrium temperature is, we can actually write the right-hand side as the sum of the C's plus the equilibrium temperature. Okay, so when I solve that for little t2, okay, I'm going to get C1 plus C2 times the equilibrium, okay, minus C1 T1 all over C2. And again, this expression I want to plug in for the T2 right there. Okay, so what I'm going to get is delta S equals C1 natural log little t1 over big T1 plus C2 natural log. Okay, all right, now when I plug all of this in for T2 here, it's going to be all of this and then divided by capital T2, which is actually just going to multiply the C2 down there. So let me write it this way, C1 plus C2 times equilibrium temp minus C1 little t1 over C2 times big T2. Okay, and what we want to do is we want to take the derivative of this with respect to our only variable that's left, T1, and set that equal to 0. Okay, and what we're hoping is that will maximize the entropy. All right, so it looks like we're out of space once again. So let me create some more space again, and then we'll take that derivative. Okay, so what I've done is I've rewritten the formula from the previous screen here. I've done two minor changes to it. Okay, one change is that I have just eliminated the subscript on T1. I'm just calling it T because it's really our only variable now. Okay, that. And what I did was I took this expression inside of the second logarithm and just wrote it as a difference. Okay, instead of a difference over the common denominator, just a difference. All right. Okay, so now I want to take the derivative with respect to T of this total entropy change and set that equal to 0. Okay. All right, so what I've got is C1. Okay, and then there's a number of ways of doing this, but I like having logarithms be unitless on the inside. Okay, so I'm just going to keep these written as single logarithms. So I'm going to take 1 over the argument of that logarithm, T over T1, and then chain rule multiply by 1 over T1. Okay. The T1s are going to go away in that expression, as you might suspect. Okay, then second, C2. Okay, then I'm going to take the reciprocal of all of this stuff. All right. It's a little bit of writing there, isn't it? Okay, the reciprocal of all of that stuff. And now chain rule, I'm going to multiply by the coefficient of lowercase t, so that's minus C1 over C2 T2. Okay, and I want that to be equal to 0. Okay, all right, next step here. The T1s go away right there. Okay, so next step, I'm going to have C1 over T. Okay. And then a couple other things we're going to get to kind of cancel out over here. I'm going to get a C2 to cancel. And then I can distribute this T2 into the parentheses there. That's going to cancel out as well. All right. So let's see what we get here. C1 over T. I have a net minus that comes from this chain rule over here, so minus, okay, and I'm going to have a C1, okay, then I have kind of this composite denominator. Okay, and notice we already have this common denominator, so that can get written, that common denominator up here is really just C2, now that we get to that. Okay, so all of this equal to 0. Okay, now I can factor out a C1. All right, and let's see here. 1 over T. Okay, let me put the other grouping on the right-hand side where it becomes positive. So I have C1 plus C2 times the equilibrium minus C1 T. Okay, and I'm sorry, the numerator over here should be capital C2. All right, well, let's just cross multiply and basically get rid of the fractions. Okay, so I have C1 plus C2 times the equilibrium temperature equals, excuse me, making all kinds of mistakes here, minus C1T equals C2T, okay, or C1 plus C2 times the equilibrium temperature equals C1T plus C2T. Of course, I can factor out the lowercase t from that, and what we're seeing right away here, when I compare these extreme left and right hand sides, is that I get maximum entropy, as long as I'm assuming conservation of energy, when basically this is the final temperature of subsystem 1 equals the equilibrium. Okay, and I think we would find that that also is equal to the final temperature of subsystem 2. Okay, so again, if we are assuming conservation of energy, okay, which at this stage I think is reasonable, okay, then what we find out here is that entropy is maximized at thermal equilibrium. Okay, that's what this finally comes down to. Okay, now just a word for the math enthusiasts here. Okay, we all ought to be concerned about math to at least a little bit of a degree. The math enthusiasts are likely to tell me, well, okay, very good. What you have done is you have extremized the entropy. Okay, are we sure that we've maximized it? Maybe you've minimized it. Okay, good point to the math fans out there. My response is, well, the calculus procedure here would be to do a second derivative test. Okay, and what we would have to make sure of is that to get a maximum, we would have to make sure that the second derivative here would be less than 0. Okay, excuse me, I wrote less than or equal to. Okay, really less than 0. Okay, in other words, if we were drawing a graph, we would want it to be concave down. Okay, now I'm going to argue on physical grounds that this cannot be a minimum. Okay, because what happens is we get a minimum that is 0 entropy change if little t1 equals big T1, and ditto for little t2 equaling big T2. Okay, and that any other temperature in between, you're going to have a bigger entropy than you had before. Okay, so this extreme value we got by taking the derivative, setting it equal to 0, can't be a minimum. That means it can only be a maximum. Okay, now if it will make you feel better, please indeed go through and do this second derivative test. Okay, I just don't feel like we need to spend the time on it in our video right now. Okay, but it may be a good little exercise for you just to practice with some math. Okay, so like I said at the beginning of the video, the more general version of this comes at a little bit higher level in a statistical thermodynamics course. Okay, you don't have to make as many assumptions or as many specific assumptions as we do. Okay, so if you're headed in that direction as a physics or engineering major, then you'll definitely get to see that. But at an introductory level, I think this hopefully is satisfying that thermal equilibrium is the same as maximum entropy. Okay, at least for now. All right, well, thanks for hanging around here till the end of the video with me, and I hope you enjoy problems like these on the channel. Okay, I would appreciate it if you could give me a subscription to the channel, like and share with your classmates and others in your circle, and hope you stick around again for another video sometime where we take a look at an interesting problem from physics, engineering, or mathematics. Thanks again. Have a groovy day.